Okay, people, last video in this module. So we're going to talk about the selection rules for our simple harmonic oscillator model. That's a new concept that we need to discuss. And I'm going to give us some specific examples of this displacement scale. So we'll look at some realistic molecules. So let's do it. So we have all of this stuff here that we came up with. Our specific solution to the wave function, our displacement scale, and the properties of the Hermite polynomials. So something that happens in these solutions as we go through the math, and as it turns out, those solutions in the math manifest into a realistic physical observation. And that's what we call a selection rule. And so that dictates if a transition will be allowed or not allowed in spectroscopy. So in other words, will we observe a spectroscopic transition? Okay. And if the selection rule is followed, then we will see that spectroscopic transition. If it's not followed, then we will not. So the first one to talk about, which we're not so familiar with, is due to these Hermite polynomials. So we'll highlight some key words here. Due to the properties of the Hermite polynomials, only specific quantum numbers are allowed in this spectroscopic transition. In vibrational spectroscopy, this is referred to as the fundamental transition. So our selection rule says we can only go up or down by one quantum number at a time. So new final can only equal new initial plus or minus 1. That might not be obvious from the properties of the Hermite polynomial here, but we can work our way through those and prove that that must be so. And so we call this the fundamental transition because if you recall from our statistical mechanics, we expect almost all molecules to be in the in the ground state, the vibrational ground state, which corresponds to nu equals 0. So the fundamental transition that we observe in FTIR spectroscopy is just going from nu is 0 to nu is 1, or really rather nu is 1 to nu equals 0, right? So that's the less familiar selection rule for us, and we'll play that out in more detail as we go. And then the other selection rule, which is maybe more familiar to you, molecules must possess a permanent dipole moment to give rise to a vibrational spectrum. And so we're going to have to introduce a new operator to talk about that. And that is going to be the vibrational dipole moment operator, which gets a mu hat. And that equals the following: negative E times X, where recall X is our displacement, right? R minus RE, so how much the bond moved. And E is our fundamental charge, right? 1.602 times 10 to the minus 19 Coulomb. And so the way this works, if we look at the expectation value of the vibrational dipole moment operator, then if this value returns a non-zero value, we get an IR spectrum. If this value gives us 0, we get no IR spectrum. And there's a couple ways that can manifest. For one, that there is no permanent electric dipole moment. Or two, if we violate this condition of going more than one quantum number at a time. So notice here, we've got the final vibrational state and the initial vibrational state placed in there. Okay? So let's flesh that out in just a little bit more detail. So if we think about our oscillating electromagnetic field, which is, light, right? And we subject a molecule to this oscillating electromagnetic field. And if there is a permanent electric dipole moment, then as this molecule interacts with this oscillating electromagnetic field, the field can induce compression and expansion of our bond. Okay? So in other words, the electrical properties of this oscillating electromagnetic field and our light is directly tied to this ability to induce stretching as it's exposed to this electromagnetic radiation. So if we look in this this dipole moment operator just in a little bit more detail, what we're really seeing here is charge displacement, right? So if there is charge displacement amongst these molecules, and I'll just show that with like a partially negative and partially positive, or the other way around, right? Could be partially negative on the top, partially positive on the bottom. Then that will give us this IR spectrum, okay? And so now if we were to go and look at what IR spectrum would look like, we can see we'll have intensity on the y-axis and frequency on the x-axis that I'll note as omega, right? And recall that omega was the square root of kf over the reduced mass. So we can see the omega places us on the x value of the scale, and the value of the dipole moment operator places us on the y scale. So for sufficiently large dipole moment operators, we will get really high intensity transitions. For sufficiently small dipole moment operators, we will get small intensity transitions. The omega value is, or really where the peak appears in the spectrum, is directly connected then to the force constant, okay? So our intensity is proportional to the dipole moment. The where it appears on the x scale of our spectrum is directly proportional to that force constant. So if we look at two realistic examples here, HCl and carbon monoxide. So let's remember what those things look like. So HCl is a single bond, right, with lone pairs surrounded around the chlorine, and carbon monoxide is a triple bond. And as we can see right away, the force constant for carbon monoxide is large, 1,860 Newton per meter. And that makes really good sense, because when we think about this triple bond, we normally describe those as very stiff or rigid bonds, and we see just that with its force constant. It is a large force constant. Correspondingly, if we look at its alpha value, right, by placing in that force constant and the reduced mass of CO, we get a relatively small displacement scale, about 4.8 picometers. So now what we can see, if we repeat that for HCl, and oh my goodness, I'm too crazy on the copy paste. That should be alpha HCl. You can see we get a significantly larger value for our displacement scale for HCl, more than twice that of carbon monoxide. And we can see our force constant is about a third of that of the carbon monoxide. So HCl is a really floppy bond. It can really stretch. And as it turns out, HCl is actually an ideal molecule for the simple harmonic oscillator. If we look at the reduced mass of HCl, so MH times MCl over MH plus MCl, we can work out that this approximately just equals the mass of hydrogen, right? And we'll work through that in our activity. And so that means HCl appears as if it's just this single mass attached to some stationary wall. So in other words, that chlorine is so massive compared to the hydrogen that HCl takes on this really classic looking picture. Carbon monoxide, on the other hand, is a little bit more complicated given that their masses are much closer to each other, and carbon monoxide follows this two masses on a spring picture much better, where we've got a carbon here and an oxygen here, and because the masses of those are very similar, we'll see a center of mass that is somewhat closer to the oxygen, but we can't draw this in the same simple harmonic oscillator picture that we did with HCl. And now the last thing I've got here, these are a look at the nu is equal to 0 wave functions and the nu is equal to 1 wave functions for comparing CO to HCl. And we can see again that CO is a much tighter, stiffer spring than compared to HCl. We can see HCl is much more spread out in its value of psi squared. And similarly, now when we look at nu is equal to 1, we can see HCl is even more spread out than is CO. So really, when we're getting to this notion of our dipole moment operator, that's really related to the differences between the nu is 1 state and the nu is equal to 0 state, as noted in the way we would compute the expectation value of that. So now, that being said, if we were to go to take a real spectrum of this, it gets a lot more complicated than just these simple ideas. But as we shall see, to a good approximation, we get very, very close to their observed spectroscopic transitions using this simple harmonic oscillator model. And when we talk about this later on in the semester, we'll have to add a few extra bits here to account for realistic properties of molecules. All the same, and in particular for HCl, this simple harmonic oscillator model works really, really well at predicting where this molecule will absorb infrared radiation. Okay, folks, that's the end of this module. I'll see you in the next one.